Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 11. Predictor-Corrector Methods. Predictor-Corrector methods are a class of numerical methods used to solve initial value problems. They are especially useful when the initial value problem is stiff or when high accuracy is required in the solution. The predictor-corrector methods aim to improve the numerical accuracy of solutions to differential equations by refining predictions, offering a good balance between simplicity and precision. They combine two steps, a predictor step to estimate the solution and a corrector step to refine this estimate. The methods previously covered for solving the initial value problems can be used in combination as a pair of formulas referred to as predictor-corrector methods. Such methods involve two computational steps. Predictor steps, shown in the figure, estimate the values at the uppercase A, B, C, etc. points. The corrector steps estimate the refined values at the lowercase a, b, c, etc. points. Prediction. The predictor step generates an estimate or prediction of the solution at the next time step, typically using an explicit method, such as a Runge-Kutta scheme. This gives a first approximation of the solution. Correction. The corrector step refines the predicted value by using implicit methods or higher-order techniques to adjust the estimate. The corrector uses both the predicted value and the prior estimates to refine the solution. By alternating prediction and correction, these methods provide better approximations with potentially fewer computational resources compared to purely explicit methods. Heun's method applies the explicit Euler method for the predictor and the trapezoidal rule for the corrector steps, where y hat I plus 1 is the predicted value, fi is the slope evaluated at the prior step. F hat I plus 1 is evaluated at the predicted step. Replacing fi plus 1 term with f hat I plus 1, the corrector step also becomes explicit. The advantages of Heun's method are: Heun's method is simple and easy to employ. It is computationally less involved. It is self-starting, i.e., the initial condition is sufficient to start the forward-marching procedure. The disadvantages of Heun's method are: its global error is second-order, so the step size needs to be chosen sufficiently small to achieve estimates of reasonable accuracy. It has the same stability properties as the Euler method. The CPU time increases compared to the explicit Euler method because it requires two function evaluations instead of one. The Adams-Bashforth-Moulton fourth-order method, ABM4, employs the fourth-order Adams-Bashforth formula, AB4, for the predictor step and the fourth-order Adams-Moulton formula, AM4, for the corrector step. In this method, both the predictor and corrector steps use foreslopes to calculate an average slope. In the corrector step, the slope fi plus 1 is also replaced with the f hat I plus 1, making it this step explicit. It is possible to employ an adaptive step size control algorithm in this method. The local truncation error for the ABM4 is estimated as follows. Then, a procedure with a variable step size strategy may be applied, using the size adjustment factor calculated from. The advantages of the ABM4 method are: ABM4 requires fewer function evaluations, i.e., one function for the predictor fi and one for the corrector step, f hat I plus 1. There is no need to evaluate derivatives for all prior points. Quantities no longer needed can be shifted out. Its global error is second order. The disadvantages of the ABM4 method are: it can lead to stability problems since it is an explicit method. An implicit scheme can be applied in the corrective step, but then CPU time can increase significantly. Another popular method in this field is Milne's fourth-order method. Milne's predictor-corrector method employs a 3-point open Newton-Cotes formula for the first derivative in the predictor and a 3-point closed Newton-Cotes formula in the corrector step. The corrector step uses f hat I plus 1 instead of fi plus 1, leading to an explicit corrector step. The advantages of Milne's method are: Milne's method is simple and easy to implement. It requires fewer function evaluations, i.e., only fi and f hat I plus 1. It has a fourth-order global error and is more accurate than the ABM4 scheme. The disadvantages of Milne's method are: being an explicit method, it suffers from stability issues under certain conditions, stemming essentially from the corrector step. For this reason, the ABM4 method is often favored over Milne's method. Let us consider the following first-order initial value problem. We will use Heun's, ABM4, and Milne's fourth-order methods to solve the given initial value problems up to x equals 15. And we will obtain solutions for h equals 0.1 and compare the estimates with the given true solution. The Heun's method is the simplest of all. It is self-starting. To obtain the first step estimate, we start with the initial guess and evaluate f0. The predictor step gives y hat 1 is equal to 0.1. F hat 1, which makes use of the predicted value, is found to be 1.0903, 252. Y1 is then obtained as follows, which leads to 0.104, 516. The second step requires prior estimates, i.e., x1 and y1. We evaluate the slope, f1. The predictor step gives y hat 2 is equal to 0.213, 971. The value of f hat 2 is evaluated and substituted in the corrector step. The corrected value yields 0.2162, 788. We repeat this recursive procedure in the same manner until x equals 1 is reached. The predictor and corrector step estimates, as well as the true absolute errors, are presented in the following table. The first row is the initial value, and the next two rows were the ones already computed. We note that the average of the true absolute errors is 2.84 times 10 to the minus 4. Next, we will use the fourth-order Adams-Bashforth-Moulton method to solve the problem. For each step, we need 4 slopes from prior steps. The starting estimates are generated using the true solution, but, in practice, we will estimate these values as well, using a one-step method of the same order of accuracy or better. The slopes f0, f1, f2, and f3 are evaluated as follows. To find the fourth step estimate, we apply the predictor as shown, which leads to 0.45, 28, 028. The corrector step requires f hat 4. Substituting y hat 4 and evaluating gives 1.206, 557. Then, substitution in the corrector step gives 0.4527, etc. Note that 3 of the 4 slopes used in the predictor step, F1, F2, and F3, have already been calculated, and they can be used directly. We only need to calculate the slope of the last step, F4. Substituting F4 in the predictor step gives y hat 5 as 0.5738, 925. The corrector requires the another slope, F hat 5, obtained as 1.2130, 462. Substituting this along with the other slopes, y5 is found as 0.5738, 738. We continue this recursive procedure in the same manner until x equals 1 is reached. The computed predicted and corrected estimates, as well as the true absolute errors, are presented in the following table. The first row is the initial value, and the next 3 rows were the ones with the starting values obtained using the true solution. The next 2 rows are the estimates we have just calculated. When the table is completed, we find that the average absolute true error is 5.1 times 10 to the minus 6. To obtain the solution using the fourth-order Milne's method. This method, like ABM4, requires 4 starting values. For the initial step, the starting values were calculated in the ABM4 from the true solution. The slopes corresponding to these solutions have already been calculated. The predictor step makes use of F1, F2, F3, and Y0. The prediction value y hat 4 is found as 0.4528, 007. The corrector step needs F hat 4 along with Y2, F2, and F3. The F hat 4 value is obtained as 1.2065, 592. And the corrected value y4 makes use of y2, F hat 4, F2, and F3, and it is calculated to be 0.4527, 828. 3 of the slopes can be fetched from the prior step. We calculate F4 for the current step. Then the predicted value y hat 5 is obtained as 0.573, 893. The F hat 5 value is obtained as 1.2130, 462. And the corrected value y5 is obtained as 0.573, 877. We repeat this recursive procedure in the same manner until x equals 1 is reached. The computed predicted and corrected estimates, as well as the true absolute errors, are presented in the following table. The first row is the initial value, and the next 3 rows were the ones with the starting values obtained using the true solution. The next 2 rows are the estimates we have just calculated. When we complete the table, we find that the average absolute true error is 1.6 times 10 to the minus 6. The Milne's method is more accurate than the ABM4. However, the Milne's method can result in stability issues. With this note, we conclude this video session. That is all for now. See you next time with another topic. Bye.